Right? In the statistical classification, we could be a statically determinate system, or we can be statically indeterminate. There's actually a third classification that we'll get to here in the next video. Let's take a look at the indeterminate situation. Right? Remember, what we're going to do is we're going to count up the number of unknown forces in our basic model. We have 2 pin supports, so that means that R is equal to 4. We have X and Y component at each of those 2 supports. Then we have 13 members, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have a total number of unknowns, add those up, and we have 17. The number of equations of equilibrium we have, well, remember in the free body diagram of the joint, because they're all pinned connected members and members go from joint to joint, then we have 2 equilibrium equations in 2D, sum of force in the X, sum of force in the Y at each joint. We've got 8 joints here, so that total is 16. Now note that U is greater than N. The number of force unknowns is greater than the available static equations of equilibrium by 1. So therefore we conclude that this is a statically indeterminate system to the first degree. We have one more unknown than we have available equations of static equilibrium. Right, now, there's more than one way that something like this can happen. Here, you can argue that's because we added an extra external component to the system beyond what we needed for basic equations of static equilibrium. This example down below, we have then our R is now 3. Notice we got a roller over here and we have a pin support at the left, but we've added an extra member here in this panel, BCHG, going from B to G. So that means that M is equal to 14, whereas before it was 13. So our total number of unknowns would be 17. We haven't changed the number of joints. Now, how do I know that? Because these lines cross. How do I know that there wasn't actually some sort of pin connected there? Generally, when you look at truss systems, that oftentimes is just overlap, but you don't have the physical image of the structure, nor do you have an ability to look directly into or have an interview with the designer to understand what they were doing. It's hinted at here because all these other joints are labeled, but this one is not. If they had drawn a little circle at each one of these joints where the members are connected, that would have also been a hint, whereas there's no circle there, but we don't see any of that here. So the only hint on this particular example is we've seen this structure 3 times now, and this one does not have that joint labeled, and so that means that, once again, J is equal to 8, and that N being equal to 2J is going to be equal to 16. And once again, we have more unknowns than we do equations of equilibrium, and we end up with the same overall classification. It means we're going to have to do something else in order to be able to solve for all those unknowns. I realize now that perhaps my piece of paper was just a little bit below the screen. Now, this stage of the course, you don't know why this is so significant and what's going on here. We got one more classification we're going to look at, and then we'll talk a little bit about why this matters so much.